Hi, this is Steve Mickey with WS Thermal Process Technology, and I'm here to talk to you about the future of gas heating in industrial furnaces. Nobody knows exactly what the future will look like. Some things will change, while others will remain the same. Economics will continue to be important because everyone always wants to save money. But costs increase over time, and as resources like natural gas become more scarce, their cost increases additionally. The best way to reduce energy costs is by using less energy. So the burners of the future will need to be more efficient. This is where technology comes into play. The focus on the environment and on reducing combustion emissions will become increasingly important in the future. One way to reduce emissions is by burning less fuel, which leads us back to efficiency. But in the next 10 to 15 years, we will approach the physical limits for combustion efficiency. After that point, further reduction in CO2 emissions will only be possible by the movement to green fuels. So new burner technology will be needed to provide the fuel flexibility required to meet future emissions requirements. Revolutionary NOx reduction technology has already existed for quite some time, but it is continuously being refined to meet increasingly stricter requirements. So, as always, technology will provide the solutions to the challenges that we will face in the future. Here we have a graph showing combustion efficiency as a function of exhaust gas temperature. For a direct fired burner, exhaust gas temperature is equal to the furnace temperature. For a radiant tube burner, exhaust gas temperature represents the temperature inside of the radiant tube, which is always hotter. So if we look at the first curve on the bottom, labeled epsilon equals 0, this represents a cold air burner with no combustion air preheat. So if we choose a random temperature, such as 1,000 degrees Celsius, we can see that the best possible efficiency for this type of burner is approximately 50%. And that's assuming that everything is in good working order and properly tuned, which is often not the case with some of the older equipment that we see in operation. Moving up to the curve labeled epsilon equals 0.4, this represents a burner equipped with a plug-in recuperator or a central heat exchanger. With this type of technology, combustion air is preheated to approximately 40% of the process temperature. So at 1,000 Celsius, efficiencies are generally in the mid-60s. Moving up to the curve labeled epsilon equals 0.6, this represents a self-recuperative burner, where the heat exchanger is an integral part of the burner. With this design, combustion air is preheated to 60 to 65% of the process temperature. So that means at 1,000 degrees Celsius, efficiencies are at or near 75%. Finally, if we look at the curve labeled epsilon equals 0.8, this represents a regenerative burner. With this type of technology, combustion air is preheated to 80 to 85% of the process temperature. So at 1,000 Celsius, efficiencies are approaching 90%. Next, we'll compare and contrast some traditional burner types with the modern types. First, we'll look at a cold air burner. The efficiency is very low because there's no combustion air preheat. So consequently, the NOx emissions are also low. The initial cost of the investment is very low because it's simple technology, but the operating cost is very high due to the lack of efficiency. Next, we'll look at a hot air burner. This happens to be a type equipped with a plug-in recuperator. So due to the mild combustion air preheat, there is some improvement in efficiency, but it is still relatively low. However, NOx emissions are now rather high due to the combustion air preheat. The initial cost of the investment is relatively low, but the operating cost is rather high since the burner is still rather inefficient. Next, we will look at a self-recuperative burner. With this design, the recuperator is an integral part of the burner. It sits directly in the wall of the furnace, which helps to minimize heat losses to the surroundings. So the efficiency of this burner type is high. The NOx emissions can be high, but with proper NOx reduction technology, they can actually be very low. The initial investment is medium, and the operating cost is low due to the high efficiency. Now we'll look at a burner type that slots in between a traditional self-recuperative and a self-regenerative burner. This burner is actually a self-recuperative type, but it's referred to as gap flow. So instead of having one large heat exchanger, there are many tiny heat exchangers, and this roughly triples the surface area for heat transfer. So it's possible to achieve efficiencies close to that of a regenerative burner, but in a less complicated and somewhat less expensive package. So the efficiency of this burner type is very high, while the NOx emissions are still very low due to the use of appropriate NOx reduction techniques. The initial investment is high, but the operating cost is very low due to the high efficiency. Finally, we will look at a self-regenerative burner. Traditional regenerative burners operate in pairs. One burner fires while the other exhausts, and the exhaust products travel through a bed of ceramic media, which serve as a heat storage mechanism. And then when it is the other burner's time to fire, cold combustion air passes through the bed of media and absorbs the heat from it. With a self-recuperative burner, however, no pair is required. Everything happens in one compact unit. Each burner contains 6 passageways. Each passageway contains a row of ceramic honeycomb discs, which serve as the heat storage media. At any point in time, 3 passageways are exhausting, and the other 3 are drawing in combustion air. And every 10 seconds, pneumatic switching valves on the burner cycle, and it reverses the flow path. So the efficiency of this burner type is very high, while the NOx emissions are still very low due to the use of special NOx reduction technology. The initial cost of the investment is high, but the operating cost is very low due to the high efficiency. Next, we'll look at some modern recirculating radiant tube types. The first is the single-ended radiant tube, and the tube pictured here happens to be a ceramic type. It's constructed from reaction bonded silicon carbide, or SiSiC. This material has twice the heat flux capacity of an alloy, so it can withstand 110 BTU per hour for every square inch of surface area. as opposed to about 55 BTU per hour per square inch for an alloy. This material does not sag, creep, or distort. It's not required to rotate the radiant tube to counteract sagging. It's not required to support the end of the tube. Not only is it not required, we insist that you not try to support the tube, because the furnace refractory will expand and contract at a different rate than the reaction bonded silicon carbide, and you could risk cracking the tube. So it should simply be cantilevered inside the furnace, like you see in the diagram. With a single-ended radiant tube, whether it be ceramic or alloy, it's necessary to use inner tube segments to define the flow path for recirculation. The burner installed in this tube is a self-recuperative high-velocity type with a flame speed of approximately 300 feet per second. The burner fires into the tube, and exhaust products travel down the inner tube assembly. They reach the end of the tube, and they flow back through the annulus between inner and outer tube, and they reach the gap between the tip of the burner and the first inner tube. And at that point, the high velocity jet from the flame creates a venturi or suction effect to draw a portion of the exhaust gases back into the inner tube assembly, where they are recirculated several times before eventually flowing back over the heat exchanger and out the exhaust port on the burner. This leads to much better temperature uniformity, which means better product quality, longer tube life, especially in the case of alloy tubes, which are sensitive to temperature changes, and lower NOx emissions. Next, we'll look at a P-type radiant tube. It's similar in construction to a traditional U-tube, but it has a cross-connecting piece to allow for internal recirculation inside the tube. So the burner fires into the top leg, and exhaust products travel back through the bottom return leg, up through the cross piece, and they reach the tip of the burner, where once again the high velocity jet from the flame creates a venturi effect to suck them back into the upper firing leg and recirculates them several times before eventually flowing back over the heat exchanger and out the exhaust port. Here we have what's known as a double P tube. It's the same concept, but there are two return legs instead of one. So this provides a greater surface area, which makes it possible to fire a higher power burner into this tube type. These tubes are typically used in the steel industry in vertical strip lines. Next, we'll look at a temperature uniformity comparison between some conventional tube types versus the modern recirculating radiant tube types. These tests were conducted at the WS laboratory in Renning in Germany. They placed thermocouples 6 inches apart on each leg of each tube, and the goal was to measure the maximum temperature differential. Where did it occur, and how large was it? So first, they tested a W tube, and they found that the maximum delta T occurred in the first leg, and it was approximately 270 degrees Fahrenheit. Next, they tested a U tube, and they saw a slight improvement with a max delta T of approximately 225 degrees Fahrenheit. After that, they tested the P-type tubes, and they saw a dramatic improvement. delta T max was only about 90 degrees Fahrenheit. And this is due to the internal recirculation inside of these radiant tubes. Finally, they tested the single-ended tube, and the results were the best by far. Delta T max was only about 35 degrees Fahrenheit. And this is due to the fact that the recirculation mechanism is compressed into a single leg. Traditionally, there's been a trade-off between efficiency and NOx emissions. In order to achieve high efficiency, it's necessary to preheat the combustion air to high temperatures. This leads to high peak flame temperatures, which are the primary driver for thermal NOx formation. It's an exponential function, so as flame temperatures and furnace temperatures increase, NOx can start to take off very rapidly. There are a number of techniques, however, which have been around for many decades to help reduce NOx, and some of those are fuel and air staging, which is really the same concept, but you're just playing with a different leg of the fire triangle, fuel versus air. So air staging, which we use in many of our burners, you bring in a portion of the air, mix it with all of the fuel, generate a partial reaction, and release some heat. And then you bring in the rest of the air a little further downstream to complete the reaction and release some more heat. So you're spreading the heat out instead of concentrating it all at one point. This helps to reduce peak temperatures and therefore lowers NOx emissions. High velocity combustion is another important NOx reduction technique, and we use it on all of our burners. The high velocity flame creates a lot of stirring and mixing action inside of the furnace or the radiant tube. So this serves to average out temperature peaks, which also lowers NOx emissions. In addition, flue gas recirculation is another important technique, and we use internal flue gas recirculation with our burners. But the idea is that exhaust gases are very hot, but they're not as hot as a flame. So by pulling a portion of that exhaust back into the flame envelope, it cools the whole reaction down a bit and serves to lower NOx emissions. So all these techniques are relatively effective, but some applications today have extremely strict NOx requirements, and these techniques may not be sufficient to meet those requirements. But fortunately, a revolutionary technique was discovered which makes it possible to achieve much lower NOx emissions. That technique is known as flameless combustion. Flameless combustion has been around for over 30 years, but it has continuously been refined to deliver progressively lower NOx emissions. Now it is possible to consistently achieve NOx emissions below 0.07 pounds per million BTU, or 60 ppm for most applications. So it takes a lot of experience to achieve optimum results. Flameless combustion is a phenomena that occurs above auto-ignition temperature, which is generally recognized to be about 1400 degrees Fahrenheit for natural gas. But it's important to have a safety factor to ensure that any gas introduced into the combustion chamber will auto-ignite. So normally the switch to flameless combustion occurs around 1550 Fahrenheit. So a burner equipped with this technology generally has two gas trains, and one gas train is operating up to the switching temperature, and then the valve on that gas train closes, the valve on the other gas train opens, and gas now flows through a different passageway inside the burner. So it's injected into the furnace or radiant tube in a fashion that sets up a more favorable recirculation pattern. So the gas and combustion air are pre-mixed with recirculated exhaust products, and a spontaneous reaction takes place, which produces no visible flame. So by eliminating the flame from the combustion reaction, peak temperatures drop dramatically, and therefore NOx emissions are suppressed to a fraction of the level possible with the other NOx reduction techniques discussed previously. So drastic NOx reduction is the primary benefit of flameless combustion, but there are a couple of other advantages as well. By eliminating the hot spot at the tip of the burner, thermal stress is reduced at that point, and that means that critical components such as nozzles and electrodes are going to last longer. And while the temperature uniformity of these modern burner types is already very good due to the high velocity combustion, pulse firing, internal flue gas recirculation, it's going to get just a bit better by the elimination of that hotspot. Next, we will talk about the move to green fuels. This graph shows projected specific CO2 emissions over time. As you can see, natural gas combustion currently produces less emissions than electricity. Emissions from the generation of electricity are significant, but they occur upstream at the point of production, so they are frequently overlooked by the end user. As the graph also shows, we will approach the physical limits for combustion efficiency in the next 10 to 15 years. After that point, further reduction in CO2 emissions will only be possible by the movement to green fuels. Electricity will also become greener over the next 20 to 30 years, but it is by no means a foregone conclusion that the future will be all electric. Only chemical energy provides unique advantages such as high availability, high energy density, and storage capability. So we feel that chemical energy will be an important part of the green future. Of course, no one knows for sure which energy carrier will play the dominant role, so we all need to be prepared for whatever it will be. At WS, we are currently delivering burners that operate on hydrogen and ammonia, and we will continue to develop new combustion technology to meet future fuel demands. Now we'll look at a brief economic example. In North America, companies typically look at payback time when evaluating the viability of an investment. And payback time is quite simply the time for the initial investment to be paid back. And that's usually as a result of the fuel savings. However, we think there is a much better tool for evaluating the viability of an investment, and that would be net present value. It's the sum of discounted cash flows corrected to today's dollars, and in our case, the NPV depends mainly on the generated fuel savings, the initial cost of the investment, the assumed interest rate, and the assumed lifespan of the equipment. And quite simply, the investment with the highest NPV is the most advantageous. So now we'll look at the example. Assume that a company is planning to purchase a new furnace, and the furnace manufacturer has offered a base package and 2 option packages. The base package consists of cold air burners installed in U-tubes. And this furnace is going to operate at around 1650 Fahrenheit. So the assumed efficiency is approximately 55%. And as we said, this is the base package, so there is no additional investment. Now, option package 1 consists of adding plug-in recuperators to the burners and U-tubes. This leads to an improvement in efficiency, and the expected efficiency of this package is approximately 65%. The additional cost for this option is $20,000, and the calculated payback period is 1.33 years. Now, option 2 is a high efficiency alternative. It consists of replacing the base equipment with self-recuperative burners installed in P-tubes. So the expected efficiency from this option is approximately 83%, but the additional investment cost is $80,000. So the calculated payback period is 2.35 years. So which option would you choose? The knee-jerk reaction might be to go for option 1 because the payback period is shorter. But if we evaluate this from the standpoint of net present value, we can see that even over a very short and conservative assumed lifespan of 15 years, the net present value of option 2 is over twice that of option 1. So the high efficiency alternative is clearly the better investment. In fact, if we assume a gas cost of $3.50 per 1,000 cubic feet, a furnace net input of 3 million BTU per hour, and an annual operating cycle of 6,000 hours per year, we see that the plug-in recuperator option leads to an annual fuel savings of a little over $17,000 per year and a 15-year lifetime savings of a little over $262,000, which sounds pretty good. But if we look at option 2, the self-recuperative option, we see that that leads to an annual savings of over $40,000 per year, or over $607,000 over the lifetime of the equipment. And keep in mind, this example is for a relatively small furnace. So as inputs increase and as lifetime increases, which is likely for this type of equipment, the fuel savings become even more significant. So the moral of the story is payback period on its own is not a sufficient tool for making investment decisions. A complete analysis is necessary to make a well-founded decision. So in conclusion, there are a variety of burner types available with varying levels of complexity and efficiency. Combustion air preheat is the most effective method to increase combustion efficiency. Flameless combustion enables low NOx with high efficiency, so we can have the best of both worlds. We will approach the physical limits for combustion efficiency within the next 10 to 15 years. After that point, further reduction in CO2 emissions will only be possible by the movement to green fuels. The investment in high efficiency burners makes sense economically, even when gas prices are low. And the lifetime savings due to the higher efficiency are huge, often greater than 10 times the additional investment. And finally, payback period on its own is not a sufficient tool for making investment decisions. Thank you very much. And if you have any questions or require additional information, please feel free to contact me.